Merci. Hi, everyone. I'm happy to be here with you today. So congratulations to everyone, first of all, for staying awake and for being able to work so hard for so long for this one single task, and your results were amazing. We will today see the best results from each of our hubs. This means top 3 results from Romania, top 3 results from Germany, and a surprise team from Georgia, which scored top 3 globally. So I think everyone is a little bit interested in exactly how they did it. But before all that, here with me is Sasha, one of the dataset authors, who will present it to you in a little bit of details. I think you all got to know this dataset a little bit too well. But to give you a little more information regarding the context, how it came to be, and why this task. Thank you, Sasha.
Yes, thank you very much. Okay, so just to give you the big picture, where the data came from and how exactly it was obtained, I'm gonna try my best to be quick. Let's see. Okay, hopefully this works. Yeah, all right. So all of it was collected as part of the Multiply project, which stands for Multiple Languages and Eye Tracking. This is a project uniting a lot of labs in Europe and beyond, all of which collect data on reading and eye tracking while reading. So all of the labs use the same protocol, the same texts, but they translate them in different languages. So such a multilingual data set is, of course, very interesting for studying how people read, but also how people read differently in different languages. And so the idea was to collect texts that would be as varied as possible and would represent different genres and different levels of difficulty. So as you probably noticed, there were different types of texts in this data set, some of them institutional, so like really great, exciting prose, something about, juridical terms and stuff like that. Pop science, lots of literature, but different types of literature, right? Argumentative texts, and an entry from encyclopedia, so something from Wikipedia, I think. And so what happens during the experiment is that people are put in front of the monitor, and the movement of their eyes is tracked, which to me, the experimenter, looks something like this. I see this little dot jumping around on the screen, and I can tell if they're cheating and not reading. And I thought I would maybe talk a little bit about the algorithm behind this, because I think this is also like computationally interesting. The position, the gaze point on the screen is determined using the position of the pupil and this little turquoise dot, which is the corneal reflection. So the camera is filming at 1000 hertz, and there's also an infrared light that reflects from the top of the eye. And then just by measuring the distance between the pupil and the little corneal reflection, we can figure out where exactly on the screen the participant is looking, which I think is a bit creepy, but also fantastic. And yeah, the infrared light is used because in general lighting conditionals can be different, but if you use infrared, I think you can see the corneal reflection tells you where exactly the eye is directed pretty well. So yeah, that's great. Thank you to whoever came up with that technology. And what else? I think maybe I could, just a second, if I could maybe go to the next slide, that would be great. Yeah, that's great. Okay, so after all of the recording, the data looks something like this. In here you can see the dots and the lines. These represent the events that in eye tracking are generally fixations and saccades. And in order to obtain those, just as a step of pre-processing that maybe you're interested in, we used 5 movements, and if in general you're curious about the field and would like to keep on working on eye tracking tasks, I think this is an excellent place to start, because there are a lot of open source data sets that you can load directly using the library, and there are many algorithms for event detection that allow you to pre-process it, also some stuff for plotting, so this is the place to go. And yeah, I think that's kind of it. This is how we obtain the data set, and in our experience, yeah, it was pretty hard to predict the total reading time. So I'm really excited to see your solutions and to hear more about them. And in general, yeah, feel free to maybe talk to me or the other organizers about this data set more, because this is ongoing research, and actually much more data will be available in the future, because the experiment also includes multiple choice questions and demographic questionnaire, as well as psychometric tests. So actually a lot of hypotheses about cognition and processing language can be tested using this data. And after the program is over and all of the data is collected in all of the different languages, it will be available publicly. So again, if you're interested in this kind of research, stay tuned. Yep, and I think this is kind of it from me. I just wanted to also mention that I think we'll include the linguistic annotations as well. So maybe for those of you who are more interested in the language side of things, it can be fun to explore those too. But yeah, this is future work. Okay, thank you very much, and enjoy the rest of the presentation.
Okay, thank you very much for this presentation. There are two teams from Germany who should be presenting now, but I heard they have a bit of a few technical issues. So before they can join us in this stream, we will continue this presentation, and they will come back at the end of them with, well, the results in Romania were very interesting, because the top 3 teams were all made of high school students. Congratulations. I think it's actually insane how much this competitive AI ecosystem, how far it got in the past few years. Last year, there was 1 high school team in top 10. Now, there are a few bachelor's teams in top 10. And the next presentation that I want us to see is the first bachelor's team from Romania, Var Maioneză. So, Mihai Duzi, Elisa Adelina Biluță, Ana Maria Markovic, and Ionuț Andrei Luminăraru. Come here, please.
Cum nu merge?
Trebuie să dau scroll.
Hello everyone, we are Biliuț, Elisa Adelina, Duzi, Mihai, Nicolae, Markovic, Ana Maria, and Lumânăraru, Ionuț, Andrei, who is missing. We are the team Var Maioneză, a funny name, I know. And all of us are studying at the University of Bucharest. Why is this topic difficult? The reading speed differs per person. Some words are skipped. As you can see in this example, she, a very common word in Romanian, is skipped. And long words and rare words take longer, as this one. I think you haven't read it. And the context really matters in a text. And some people can have eyesight problems, which influences this topic.
We studied the data set, and again, we skipped the words whose reading time, TRT, was 0 or neighboring on 0. And we extracted the word ID, which showed us the word position, the actual word, the participant ID, who is the reader themselves, the document, and our answer, which is the reading time, TRT.
Now we are talking about our experimentation journey. First, we attempted to use a pre-trained BERT and fine-tune it. However, it wasn't the best option. We then tried global mean, world mean, and lastly we tried with gradient boosting algorithms, XGBoost, Light GBM, and CatBoost, which CatBoost turned out to be the best out of them, although the Light GBM model had comparable results with the CatBoost.
Feature engineering. So we tried to simulate how humans process the text. We looked at the word length, the capitalization, the punctualization. We looked at the context features, the words before the word that is read in the moment, and the words that would follow that word. The position features, as in page and text, and the frequency features, the common words versus the rarer ones.
So our final architecture is firstly the data set, then we have the feature engineering that she talked about earlier, and then we have a ensemble of models, the main one being the CatBoost, but then we also used a TF-IDF ridge on character n-grams between 2 and 5. The same thing we did on words, a TF-IDF word ridge. And lastly, we had a prior model. We then made the weighted ensemble, each model having a weight between 0 and 1, the sum of the weights, of course, being 1. And then using the weighted combination of models, we generated our final prediction. And in conclusion, we learned that feature engineering is more important than the model complexity, and most of the times model complexity doesn't make results better.
Vino cu pețe.
Stai un slide, să zic mulțumesc și gata.
Și că am găsit inspirație, da.
Thank you for your attention. We also found 5 ducks, and the students are Viuță Elisa Adelina, Duzi Mihai Nicolae, Marcovici Ana Maria și Lumânăraru Ionuț Andrei.
Team Var Maioneză out.
Thank you for your presentation. Our next team, the first place from Romania, it's called Pre-trained Language Models. This team is from Cluj. It's not physically here with us. Răzvan Andrei Stan, Matei Tudor Pop, Jan Ștefan Cazacu, and Vlad Andrei Rus.
target distribution, and you can see that a lot of words from targets are being skipped. And the rest that isn't being skipped is very left skewed. This made us think to a very simple solution to just build two classifier models at first, one that would classify whether a word is skipped or not, and one that then, after that classification, can do the regression on the specific time for the word. To handle the skewedness, we just logged the values. It wasn't that big of a deal. Here's
Sorry, can you wait for a second? We can't see your screen actually.
You cannot. Okay. It's a bit odd. Excuse me for 1 second. we are back then. And I won't introduce us for the third time. This is our team. We are the team pre-trained language model. And now that you do see the share screen, it's brilliant. Okay. Here is, okay, so we are using a hypermodel for TRT prediction. Our goal is to predict the word level total reading time for unseen Romanian readers. And the final solution combines text complexity, contextual language, model signals, visual layout features, and extreme eye tracking statistics. But first, let's dive into some plots. The first plot that we stumble upon is the target plot, and as you can see, many words are entirely skipped, which got us to think that we'd achieve much better accuracy if we trained two different models, and that's what we did. We trained a model to classify whether a word is skipped or not, and then we trained the classic regression model. Now, if you were to ignore the skipped part, we see that the data is quite left skewed, and because of that, we applied some log scaling to it to make it more friendly for our model. We also plotted the participant ID, and you can see they quite vary. This is mostly to show that we are not having the same participants and that we have to try to debias our reading times in order to achieve the optimal solution. Okay, we have a total of 160 features, all extracted from the text, which are features such as the word length, such as its shape, such as the number of digits, the number of upper characters, all sorts of features. We had plenty of time this afternoon to brainstorm these ideas, and these features together are being put in a data frame. Then we are fitting into three main models, and we are combining the prediction of these three models. And here's the target distribution after processing. As I said, we kind of avoid skewness a bit using log, and by dividing our data into two separate classes, the ones that are being skipped and the ones that aren't. Now I'll let my colleagues continue from here. We have
the data linking strategy, which implies that the word ID encodes text, page, and word index. This is very important because allows test and train rows to be joined with lexical properties, extremely fixation data, and EOE data files. Each word is represented with linguistic, contextual, visual, and external reading signals. You will see later what I mean more exactly.
Okay, here's the AI layout features. Now, this is a very interesting idea that we've gotten, and that is that the reading is highly influenced on where the word is placed on the paper. And because we've gotten the data necessary to determine such features, we know the page, we know a lot more from the data set than just the word itself. We were able to transform those information into trying to put them into such rows as this, and this gave us our model a lot of information about how fast the such word is going to be read.
Yes, because as you can see, it's very important that we had the chance to fit the text based on its length. We had the chance to fit in its rectangular like page. When we only had like words to put in a very long sentence, we found a way to differentiate each row by the length of the word, as you can see.
Why this layout matters, as we've said, reading is spatial, and the eyes move more throughout the lines using fixations and saccades. Words near the line start or line endings can have different fixation patterns or layout features and information that purely textual model cannot observe. This was by far our biggest improvement in the code, and this is probably what got us quite a high accuracy. So this is what it's mainly focused on. Of course, the other features were also quite important, but this also helped our model quite a lot.
We used for the last step cat boost for the regression, and it handles all the features that are tabular. lexical n-grams, the BERT embeddings, and the layout features. And we tried several seeds to reduce variance. And beyond that, we used an ensemble composed of multiple regressors like Hubert regressor, Ridge, and random forest to finish the job for this. Also, the local validation is very important because we also had the advantage that you gave us the validation function at the start of the problem. It was very helpful for us and really told us in what direction we should go with our code, our submissions, and our way of thinking, actually.
This allowed us to save a lot of submissions and to be able to correctly evaluate our model before submitting a file directly on the platform, thus giving us an advantage. We also have some prediction distribution, which shows that our model does learn and does make the predictions accurately based on the training data. We can see we have the almost the exact same distribution here with some left skewness over here. It overlaps quite good, and this was also a way of validating our model. Of course, not as accurate as the function itself. We also have reproducibility. We have the same script, of course, and we have the same seed, but I considered it quite important to mention. In conclusion, the solution treats reading time as a hybrid signal from language, constant visual placement, and reader behavior, and some AOI layout features which make the model aware of where the word appears on the screen. The final blend, of course, is optimized directly for the competition metric. Thank you for your attention. This was us, and I hope you enjoyed it, and I hope you learned something from it, because that's the more important thing. Thank you.
And before the presenters present their work, I want to thank Marina, Chris, Ilyanka, and Anton, including Sinan, for this opportunity to co-host this event in Heilbronn. So yes, thank you. And before the presenters present their work, I want to thank Marina, Chris. Sorry. Yes, so moving on. So the third place from Heilbronn Hub is Team Toucan Dumplings. Unfortunately, they are not here. to present their work. So we'll move on. And on the second place is Kung Pao Chicken. They are also not here to present their work. So I will announce the first place. So the winner from Heilbronn Hub is Mikey Hacks, and I would like to say congratulations. And yeah, once again, I would like to apologize for the delay, and I will leave the stage to the team. They can introduce themselves and talk about their work.
Yes.
Okay, great.
Hello, Janis coming too. Everyone coming. First of all, so as we cannot hear you, we don't have the rights to share our screen, and we'd noted like to show the code base
and the visualization.
Yes, and the charts. So if possible, if you have the opportunity to give us, we can't see you. Please request to speak on a laptop with the screen.
What? Oh, okay.
Okay, Hackathon. You can just show this one, or yeah.
Okay.
Can you hear us now?
Yeah, I believe it works.
Wait, let them give us feedback first before we present, so they can hear us.
It works. So I guess we should introduce ourselves. My name is Yanis. I'm a second semester student at TUM BIE.
And I'm Nicolas Marcia, also second semester at BI.
And I'm the second semester. My name is Luca. And I guess we're gonna start with Janis.
Yeah, Yanis. So firstly off, one of the first things we did was we analyzed the data and we found some patterns. Firstly off, I mean, the word length is, as was noted, it was strongly correlated with the reading times. But what we found was that after a certain amount of characters, the word length grew a lot. In this case, it was 5 characters. Likewise, if a word was under 3 characters, it was almost always going to be skipped. We also noticed that different text types have aren't exactly the same. For example, these are the argumentative, these are the 5 text types that were presented to us in the data set. In the training set, actually, the encyclopedic one and the PopSci one weren't present, and as you can see, they're slightly different, so we just removed them from the training data. Likewise, one of the things that actually got us a lot of points was the syllable counts. Words with 0 syllables, or in this case, I guess 1 syllable, are almost always going to be skipped. And likewise, words with more syllables tend to be read out a lot more. Furthermore, another thing we noticed is that the placement of the word next to other words matters a lot. It is not as big of a correlation, but for example, words that are placed next to previous words which are longer or have a higher value of reading time tend to be skipped more often or tend to be read faster. Same exact thing happens with the next words, and we use these parameters as well as other ones, such as whether it's punctuated and really many more to make a model. So about the pre-processing,
Okay.
Nicholas.
So getting the word length and the frequency was quite easy. Now the problem was how could we divide the syllables, and we searched on the internet and we found a lot of rules in Romanian that could actually help us separate them. And we don't use the straight frequency, we use the logarithmic base, because we found out that even if a word, the counting gets up, at some point it will, let's say, become constant, because the viewer cannot read even faster. It hits a plateau. And we also use some other features. For example, if it has a punctuation, if there are clips, if it's on URL, that's a separate class. Also, if it's a digit or a number, it's also another case. And we also have about 30 other features.
Yes. So now I will just quickly about not the data, but about the model, talk a little bit how we approached it. So first we split the problem into two sub-problems. That means we're not trying to directly predict the reading time, but first we're trying to see whether the word receives a meaningful reading time, and then if it does, how long does it take it, and then later we're like multiplying it to get the probability. And then, so for every word, we compute the weighted positive probability that participants give a positive reading answer. And after that, we see how good the average reading time among these answers is. Our regressor, 1 second. So you can see here is 35% extra trees and 65% cat boost. We thought of using cat boost because it's not really a linear problem or tabular prediction with many nonlinear features like zero values or like little URLs. And so we thought that gradient boosting might be a good approach. And then finally, we're multiplying the probability by the predicted reading time, which gives us then the reading time for our word. Finito? Okay, then I think that's it from our side. Thanks for listening. I hope you enjoyed. And also from Germany, congratulations to all the teams in Romania. Well done.
Congratulations again to all of you. Now the team team that should present now is a team that was a bit unexpected. I mean, it's not unexpected, it's just a bit unofficial. The third team globally, Team Geek from Georgia, made out of Nicolas Jejenava, Nicolas Kipshige, Antoni Ingorogva, Georgi Kavelashvili, and I'm sorry if I mispronounced your names, but feel free to present.
Okay. Hello, we are Team Geek, and today we'll present the third place solution for the Nitro NLP Hackathon. So the task is to predict the average reading time of text in Romanian. So something interesting is that train and test had completely different speaker IDs and texts. So because of that, we decided to throw away the speaker ID and just do mean TRT per word. Also, we found external data to use it, and they had the same passages as the training data. And we used TAP-PFN, which is Tabular Foundation Model, which is based on pre-trained transformers. And this is state-of-the-art for small data tabular regression tasks. So as the external data, we found some research paper from GitHub, which is the Romanian eye tracking corpus. And it contained exact passages from this hackathon, and every word in trained tasks was covered in corpus. We used its data and actually enriched our training corpus to make our model generalize better. We also made handcrafted features such as word length, frequency, which was based on the zips flow, and most importantly, entropy of the previous and next word. And other features were also made to actually help the model generalize and give a better training signal. Also, we observed the plot and we saw that target was right skewed, and it produced some kind of long tail, which was why we used logarithmic transformation on the target. And it actually compressed the long tail and kept the zeros mapped to 0. For the pre-trained models, we used Romanian BERT to extract per word log contextualized embeddings and compress them using PCA to actually reduce dimensions. And we trained small regression head on top to predict logarithmic scores for the target. Additionally, we use Romanian GPT-2 for per word entropy, and the model's negative log probability of each word in context, it was a classic predictor of fixed time. Yeah. And also we use open source LLMs using in-context learning to predict per word TRT. Additionally, we use the TAP-PFN model, which is a special, as I said, special pre-trained transformer used for small data tabular regression tasks. And it worked very well on this competition, as our intuition told us to. The final ensemble contained other gradient boosting models, except the TAP-PFN, such as LightGBM, XGBoost, and CatBoost. And finally, we had 65 features, which were generated using 4 families of methods, and we finally trained this ensemble altogether. The main thing we learned from this competition is to not trust the leaderboard, but the leaderboard A, and like create strong validation setup to actually see how our model works on other subsets. And we couldn't create this strong validation setup, which is because we are lazy to do. Yeah. Thank you very much.
Thank you. That was an interesting ensemble. Okay, and now we are finally getting to our top 2 teams, which were neck to neck this night, as far as I've seen them. The second team, Dream Team, congratulations, Mihnea Teodor Stoica, David Tache, Tudor Morariu, Răzvan Matei Dedu. Nu vi l-ați pus pe drive? Ce? Ba da, le-am pus pe drive. Păi e drive aici. Ah, ok. Trebuie să stai după, în dreapta paharelor. Așa. Așa, asta este microfonul, vorbiți în microfon. Și unde e drive-ul? Îl pun eu.
Hello, everyone. As you know, we are a dream team, and we would like to present our solution. This task... Okay, this task consists in predicting the total reading time for specific words in Romanian. What we first started with was analyzing the data, the length of the data set, the number of training rows, test rows, training word IDs. We noticed that in the data there were multiple words that were the same, with the same IDs, but with different speakers, so with different readers. So what we did was we took the mean out of for each word the amount of time, and then we dropped the rest of the columns. Next up, we calculated some statistics, and we noticed that 30% of the data was labeled 0. Our pipeline consisted in the following. First, we aggregated the training labels by word ID. Then we used an external data set, which we sourced in this PDF. We extracted the labels and we added them to the final features. After that, we used Roberta to pre-trained Romanian BERT to calculate the embeddings of the words. We also tried using attention heads, but it didn't really work. And then we reduced all of these components with using PCA to 128 components. The most important features that we calculated were the word length, as stated in the statement, capitalization, punctuation, vowel, consonant count, syllables, frequency, affixes, and word shape variance. We also used position features, like the word ID also encodes the page and within page position, which turned out to be pretty important. And also we used local context features, such as previous next to one word and two word values. We took consecutive words and just added them into consideration. These are some additional plots, like the correlation matrix and the auxiliary fixation coverage by source file and auxiliary total reading time versus training mean total reading time. For model and training, the target is transformed as that following formula, which makes the regression problem less dominated by very large total reading times, which were very unique. This is the final light GBM configuration that we used in the final submission. And these are the statistics, the results of our models. These are some additional plots. This is also, after making the predictions, we looked at the mean TRT by participant, but we actually realized that was just noise. I also tried to reverse engineer the data set we found on the internet, because it was the same as the training and testing data. Yeah, but it was altered with the noise. You put like random noise with the participants, right?
We also tried using the pre-trained models that were put in the release page, like the 2 versions of BERT, but they didn't really work out.
Okay. Some limitations were the fact that there was the data was very noisy. Different participants got extremely different results. Some of the words were skipped, some of them weren't, but we managed to temper that by making the mean out of each participant. Regarding the source code, it's pretty reproducible. We try to write it as structured as possible. And that's kind of it. We use NumPy, Pandas, standard libraries. And ChatGPT was used to help to draft and organize this write-up and the code presentation. And for references, it's a really long list. We gathered a lot of resources. Yeah, that's kind of it. Thank you very much. Thank you.
Thank you. I will give you your diplomas after. Okay, great. And now the first team overall in this competition, which is made out of Well, people who competed internationally at the AI Olympiad, coaches from Cram School and Algolimp, and people who competed here. You can correct me if I'm wrong. Okay, actually, I think you better introduce your team. 6 șeptari. Ștefan Alexandru Asandei, Laurian Iacob, Andrei Ciorteasuciu, David Gheorghică Israte. Congratulations.
I won't ask why. Hello guys, so we're the team 6 șeptari and today we're going to introduce to you our solution. So our team is made up of Stefan, me, Laurian and Andrei. Stefan and Andrei weren't able to be here right now, but I want to greet them and say that it was a long night, but it was all worth it. So let's get into it.
So we will start by taking a look at the data we are given. Starting with the training data, we got 100K observations, 30 participants, 2,000 unique words, 9 texts, and we had, very importantly, 30 values that were skipped, 0 data. And compare that to the test data, we had 9,000 observations, 5 participants, and 1,000 new words, completely unseen in the training data. We use this metric to evaluate during the competition.
Okay, next
now let's take a look at the architecture of.
It's mine, sorry. Okay. So basically what we're going to talk now about is about what we've used externally outside of the competition because we were allowed to use external data sets. So as many of other participants observed, you could find externally the data set that was in the test set. But after a quick sample and looking at the data, you weren't able to reproduce the noise, and so using it would just mislead you to another solution. So that would be a big no-no. Don't use that. It will only hurt you. And so we've tried to analyze the data. Mostly this task was about feature engineering and improving and finding as many features that were correlated. Because there were other participants, you could not look at the features that would represent a person. You would need to look at some local features that are generalizable. So basically what we've seen and observed, and I guess many of you participants were able to observe, was that 76% of the words that were in the test set were not in the train set. So we needed to improvise. What we did here was look at some data sets from some online data sets that we would use to get some frequencies. So basically we've used Corolla and WordFrag to extract the data, and after we've taken a large language model to do some other feature engineering, which we'll be talking about in the feature engineering stage.
Okay, so let's talk about what we tried, what worked, and what didn't work. The conclusion of the data was that transferability beats expressiveness. So the things that basically got in our way and stopped us were the stop words from the training labels. They had all 0 values. Other problems we encountered were reach on training word embeddings, which led to CV leak, per text calibration that didn't work due to the distribution mismatch between the training and the test, as well as ensembles and meta learners weren't that good due to the fact that they had blind spots. On the other hand, what survived and we have in our final submission are pattern-based heuristics, so we don't get any label dependency, using external corpus to cover 98% of the language used in both test and train. Contextual language model signals were also used, and our 2-stage architecture. So let's talk a bit about the 2-stage architecture. We basically broke the problem in 2 sub-problems. The first part was to determine the probabilities of a word to be skipped. And we used Casboot classifier to get a probability, and we basically decided that we are going to give up on words, depending if the probability was below 51, if I'm correct, due to the confidence of the model, we considered that. And the words that survived and we considered that would be read, we put them through a regressor that had a lot of feature engineering. what did this two-stage architecture model achieve? Well, it managed to solve the fact that we had a very inflated, a zero inflation data set. These values could not have been ignored.
Okay, perfect. Thank you. Now let's turn into feature engineering, the most important part here. So basically, we've employed over 186 feature engineering techniques, but here we're going to talk about the most relevant. So firstly, as I've already mentioned before, 76% of the words in test were not in the training set. So we've taken things externally. We've searched at some other corpora and looked at the frequencies of some words appearing in other data sets, and after log them because, well, words in a billion, a word in a billion token corpora is too much, so we needed to extract them. And so basically, we've looked at the logarithm of the probability of a word appearing in a corpora, and after did some feature engineering, as you can see here. Mostly we've logged them, we looked at the maximum frequency, we've correlated between two data sets, Corolla and WordFrec, and after we've put them together, obtaining a 90% accuracy. Okay, next. Okay, another interesting feature engineering that we've been able to achieve was the word length and context. Okay, so as my friend already mentioned here, you could see that it did not matter what the document it would be, you would have a 30% skip rate. So 30% of the words were skipped. Now we had many theories about it. We first started to think that it was because of the stop words. So stop words like and, by, the, etc. were words that you would skip naturally because you do not care about them. But as we've proven by some trial and error, we were... Okay, so by trial and error, we've been able to see that it did not help at all. So we've implied an architecture that does not use hard labeling, but soft labeling. So here we have, can you put a parenthesis here? Okay, so we have a model that classifies if a word is skipped or not. This is the probability here, and we've made 1 minus this probability. Okay, so 1 minus the probability to see if the word was in fact skippable or not. After we've multiplied by the Euler number to the power of the logarithm of the total reading time. Why logarithm? Because the distribution was skewed. So you would have something like this, and we do not want stuff like this, so we logarithm them and did this, which increased the accuracy by an R squared of 0.1, which is in fact a lot for this competition, where the scores were in a range of 0.36 and 0.41. Next. Another interesting thing that we did here was to get the surprisal score. So basically, we've deployed a large language model to predict using masking of some words to get how expected was that word to come, because naturally, when you're reading some text, you might think, am I expecting this word or not? Because in literature, if you do not expect to see something, you would be shocked. You would need to reread it maybe once or twice to understand what is happening here, yeah? So we've deployed a large Roberta language model to get an embedding dimension of each word and do some masking to understand what word is expected or not. After we've reduced the dimensionality and employed them as features. Unfortunately, these features were not that significant for our model, but it did still help that surprisal score, as you'll see in the fourth slide of feature engineering. Here we've employed some of the most important features. So basically, as you can see, the logarithm of the word frequency is the most important feature that you can see here. And more importantly, an observation that I want to make here is that if you employ participant-specific features, you would overfit. So it is at utmost importance to not do that. So there are people who got their scores on the complete data set decreased because of that. So don't. Just look at the features and the context, maybe some window, but do not employ some means or scaling based on that because the distribution is skewed. There are other participants, and other participants read differently. So please don't do that. Now let's look at some validations because that was a struggle as well.
Yeah, so we were very afraid that we would overfit, so we had to employ some measure to not do that, and we decided to go at first with a group K-fold. Basically, we took the 30 participants, folded them into 5 groups of 6, and trained on 24 and validated on 6. And this, as my colleague said earlier, caused the following problem. Because there were only 2,000 unique words, each word was read at the same time by both a person in the validation and in train. And that caused the following thing, because as we saw, the features are related to the word more than to the person to reading it. And this resulted in words that were supposed to this caused the problem when we had new words, because we didn't know the features on these. So we employed the following technique.
Okay, thank you. So what we did here, and what was the most important thing for our validation and not what were fit, was a cold start technique. So basically, we would split on false the data set, but not randomly, based on documents. So we would split on 80% of the documents to be on the train, and after 20% to be on the validation. And by that, you could not employ some mean statistics, because realistically speaking, some text would have a mean, and that mean would be used, and it would screw how the data set is perceived by others, and so it would ruin everything. If we can go to the other slide here, you would see some comparison. So basically, a participation split would give a score of over 45, which was not achieved and would lead to to overfitting, basically because it was not achieved in a competition of 45 score. Then we did a cold start. If it was over 41, it would be too much, and it means you overfitted as well. But if you had the range between 40 and 41, it means that it was something relatable and transferable, mostly. And here we've uploaded some versions of our data. So the first version of our data and our baseline was a paper found from Unibook, which had a similar task in mind. And we've taken that paper, tried to implement it. It took kind of 1 hour to do that, and we've obtained a score of 0.38. Okay, thank you. After we've tried some other stuff, some feature engineering, here we also tried some neural networks, deep neural networks. Mostly we focused on transformers and long short-term memory architectures, but guess what? It was too little data to do that. So this tied with the cross-validation overfitting, it blew our socks off. It was not good at all. After we've tried doing some stop words, as I've said before, we tried some hard labeling on the stop words. It ruined our data set at all. It was not good. After that, we had another idea, because if you looked at the test set, it was only scientific papers, and the train set had scientific, had some literature in it, and we've tried to remove that, because if you would look at the distributions after the mean of some encoder-based models, you would see that the distribution are at all different. But if you're training on that, it would mean that it does not generalize, and it screws the data set, because
Only one scientific paper was used from Wikipedia, I think Wikimoon.
Yeah, Wikimoon. Yeah, after we've implied the winning solution, which was the soft labeling plus the logarithm and a lot of feature engineering. By the way, a huge thank you to the commission who set the submission rate. We sure had a lot of fun doing that. Please don't do that again. And after we've tried some other solutions about correlations, about the marginal, we've tried to fine-tune the cat boost with Optuna. It took 5 hours. No. And yeah, I think that's it.
Yeah, thank you, I guess. And
thank you.
Have a nice day.
Bye, guys.
Thank you. Okay, I still have some special awards, very fast special awards. First of all, the Duck Hunter certificate for Dulgheru Ștefan, who found the most ducks during the duck hunt. Okay. Second of all, so this hackathon, and not only this hackathon, everything we did for the past year has only been possible with the extensive work of our volunteers. So I want to have a short shout out for the volunteers who proved themselves the most this year. First of them is Anna, who wasn't here today, but she was here at all our, well, yesterday and all our other events, and she is the one who sent most emails, and many people already saw her a lot. And second of them is Andrei Lascu, who is here with us. Așa. Okay. And I want to thank our volunteers from TUM, who also got involved in this and worked a lot to make it happen. Thank you, Ilinka, thank you, Antonio, and the organizers, Denia and Sinan, thank you so much. It's amazing that we are finally at an international level. We are so happy that you organized a hub in TUM for us, and we are expecting so many more hubs in the next year. We started talking with a few more universities from different countries, and we have a lot more things, more surprises planned for you next year. I think the level that everyone got to is extraordinary, and I can't wait to see what you will do next. Congratulations.